Hey everyone! Tonight we're diving into something that will completely change how you picture our planet. What if I told you that everything you think you know about Earth's geography is basically a snapshot from just the last few million years? What if the continents weren't always scattered across the globe like puzzle pieces thrown by a cosmic toddler? Tonight, we're rewinding the clock on our planet, way back to a time when you could literally walk from New York to Morocco without getting your feet wet. Before we get started, take a moment to like this video if you're genuinely curious about our planet's hidden past, and let me know in the comments where you're watching from and what time it is there. It's always fascinating to see how our global community comes together to explore these incredible stories. Now settle in. Maybe grab something warm to drink, because we're about to journey back hundreds of millions of years to witness Earth in a form so alien it would be unrecognizable today. Picture this. No Atlantic Ocean. No Pacific as we know it. No Mediterranean Sea sparkling between Europe and Africa. Instead, imagine one massive landmass, so enormous it stretched from pole to pole, surrounded by a single, endless ocean that made our current Pacific look like a backyard pond. This wasn't science fiction. This was Earth, roughly 250 million years ago, during the age of the supercontinent Pangaea. But here's where it gets really wild. Pangaea wasn't just some random arrangement of continents that happened to bump into each other. It was the culmination of an epic geological drama that had been playing out for hundreds of millions of years. A slow-motion collision of continents that created mountain ranges taller than the Himalayas and deserts more vast and brutal than anything our modern world has ever seen. The story begins with a German meteorologist named Alfred Wegener, who in 1912 made an observation that would revolutionize our understanding of Earth itself. Staring at a map of the world, Wegener noticed something that probably thousands of people had seen, but never really thought about. The coastlines of Africa and South America fit together like pieces of a jigsaw puzzle. Not kind of, not sort of, but with an almost perfect match that seemed far too precise to be coincidence. But Wegener didn't stop at just looking. He dug deeper, and what he found was absolutely mind-blowing. Identical fossils of ancient plants and animals appeared on continents now separated by thousands of miles of ocean. Rock formations with the same age, composition, and structure lined up perfectly when you mentally push the continents back together. Mountain ranges seemed to continue from one continent to another, as if they had been split apart by some colossal force. Wegener called his theory continental drift, and he proposed that all the continents had once been joined together in a single supercontinent he named Pangaea, from the Greek words meaning all Earth. The scientific community absolutely destroyed him for it. They ridiculed his ideas, questioned his credentials, and dismissed his evidence as coincidence. The problem wasn't that his evidence was weak. The problem was that nobody could explain how continents, these massive chunks of rock, could possibly move. It would take another 50 years and the development of plate tectonic theory before Wegener would be vindicated. Turns out, Earth's outer shell isn't one solid piece. It's broken up into massive plates that float on a layer of partially molten rock, constantly moving, colliding, and separating in a dance that's been going on for billions of years. These tectonic plates are the engines that drive continental drift, and they're the reason why Pangaea could form, exist, and eventually break apart. So let's travel back to when Pangaea was in its prime, roughly 250 million years ago during the Permian period. If you could somehow hover above Earth in a spacecraft during this time, you'd see a planet that would make your head spin. Instead of the familiar blue marble with its scattered continents, you'd see a world dominated by a single C-shaped landmass that stretched from the North Pole almost to the South Pole. This supercontinent was absolutely massive. We're talking about a landmass that contained virtually every piece of dry land on Earth. North America, South America, Africa, Europe, Asia, Australia, Antarctica, all mashed together into one continuous piece of real estate. The scale was so enormous that if you stood in the center of Pangaea, you'd be further from the ocean than any place on Earth today. We're talking about interior regions that were over 2,000 miles from the nearest coastline. Surrounding this continental giant was Panthalassa, the superocean that makes our Pacific Ocean look like a small lake. Panthalassa covered roughly 70% of Earth's surface, an endless expanse of water that wrapped around Pangaea like a cosmic moat. Within this superocean, there were smaller bodies of water, including the Paleotethys Sea, which carved into Pangaea's eastern edge like a massive bay. But here's where things get really interesting. The climate of Pangaea was absolutely brutal, unlike anything we can imagine today. Those vast interior regions, thousands of miles from any moderating ocean influence, experienced some of the most extreme continental climate conditions in Earth's history. We're talking about temperature swings that would make the most extreme desert climates today seem mild by comparison. During summer, the interior of Pangaea baked under intense heat, with temperatures that likely exceeded anything we see in modern deserts. But winter brought the opposite extreme, with bitter cold that could freeze vast regions solid. The seasonal temperature variations were staggering, swinging 14 to 16 degrees Celsius, similar to, or even more extreme than the harshest continental climates during the Ice Ages. Most of Pangaea's interior was essentially one enormous desert, probably the largest desert system in Earth's entire history. This wasn't like the Sahara or the Gobi, which are big but still have boundaries. This was a continental-scale wasteland that stretched for thousands upon thousands of miles, broken only by occasional mountain ranges and the rare oasis where underground water managed to reach the surface. The mountain ranges themselves were absolutely spectacular. When continents collide, they don't just bump into each other gently. They crash together with unimaginable force, crumpling the Earth's crust upward into massive mountain chains. The collision zones where the pieces of Pangaea came together created some of the most impressive mountain ranges in Earth's geological history. One of these ancient mountain chains still exists today, though it's a shadow of its former glory. The Appalachian Mountains, which stretch from Canada down through the eastern United States, are the worn-down remnants of peaks that once rivaled or exceeded the height of today's Himalayas. Over the past 250 million years, erosion has ground these ancient giants down. But in their prime, they were absolutely massive, creating barriers that fundamentally altered weather patterns across the continent. Another major mountain range, called the Central Pangaean Mountains, ran east to west across the supercontinent's equatorial regions. These peaks created a massive barrier that disrupted atmospheric circulation patterns and contributed to the extreme climate conditions that made much of Pangaea's interior uninhabitable. The formation of these mountain ranges wasn't just a matter of pretty scenery. These massive uplifts fundamentally changed how air and water moved around the planet. They blocked weather systems, created rain shadows that extended for hundreds of miles, and channeled atmospheric currents in ways that created the extreme climate conditions that defined life on Pangaea. But not all of Pangaea was a barren wasteland. Along the coastlines, especially near the equator where the climate was moderated by the surrounding seas, conditions were dramatically different. These coastal regions, particularly areas that remained close to the Tethys Sea, supported some of the most lush and productive ecosystems in Earth's history. Evidence for these ancient tropical paradises still exists today in the form of massive coal deposits found across the United States and Europe. Coal forms when plant material gets buried in swampy, waterlogged conditions and is slowly transformed over millions of years into the black rock we burn for energy today. The thick coal seams found in places like Pennsylvania, Illinois, and parts of Europe are direct evidence of vast tropical forests that once thrived along Pangaea's coastlines. These weren't just ordinary forests. We're talking about tropical swamplands that supported giant club mosses, tree ferns, and early conifers that grew to enormous sizes. Picture trees that towered hundreds of feet into the air, their massive trunks disappearing into canopies so thick they blocked out most of the sunlight from reaching the swampy forest floor below. These coal-forming swamps were incredibly productive ecosystems, teeming with plant and animal life. The warm, humid conditions near Pangaea's coastlines created perfect growing conditions for vegetation, leading to an explosion of plant life that would eventually become the fossil fuels we depend on today. The contrast between these lush coastal regions and the harsh interior deserts was absolutely stark. You could travel just a few hundred miles inland from these tropical paradises and find yourself in some of the most inhospitable terrain on Earth. It was like having the Amazon rainforest and the Sahara Desert as next-door neighbours, creating ecological boundaries that were more extreme than anything we see on our modern planet. This dramatic climate variation had profound effects on the evolution of life during the Pangaea era. The assembly of the supercontinent created conditions that favoured certain types of organisms, while making life incredibly difficult for others. The increasingly arid conditions in the interior regions favoured the evolution of animals and plants that could survive with limited water. This was the time when reptiles really began to diversify and thrive, developing adaptations that allowed them to survive in dry conditions that would have been lethal to their amphibian ancestors. It was also when seed plants began to dominate terrestrial ecosystems, their seeds better adapted to survive in the harsh, dry climates that characterized much of Pangaea's interior. But the formation of Pangaea wasn't just changing life on land. The assembly of the supercontinent was having catastrophic effects on marine ecosystems as well. As the continents came together, they eliminated vast areas of shallow continental shelf seas that had been the primary habitat for most marine life forms. Ocean circulation patterns were fundamentally disrupted by Pangaea's massive size and north-south orientation. The normal mixing of warm and cold ocean waters that had maintained stable marine ecosystems for millions of years was suddenly cut off. Warm equatorial waters became trapped in the Tethys Sea and other enclosed basins, while cold polar waters were prevented from circulating into tropical regions. This disruption of ocean circulation had devastating consequences. The warm, stagnant waters in enclosed basins became depleted of oxygen, creating dead zones where most marine life simply couldn't survive. Water temperatures in shallow areas rose above the tolerance limits of corals and other temperature-sensitive organisms. The result was one of the most severe mass extinction events in Earth's history, the Great Dying that occurred at the end of the Permian period. This extinction event wiped out roughly 96% of all marine species and 70% of land species, making it the most severe extinction event our planet has ever experienced. The formation of Pangaea didn't just reshape Earth's geography, it fundamentally altered the planet's climate, ocean circulation, and the evolution of life itself, setting the stage for dramatic changes that would continue for hundreds of millions of years to come. But life, as it always does, found a way to adapt and survive, even in this transformed world. The creatures that managed to endure the Great Dying weren't just lucky survivors, they were evolutionary pioneers, developing innovations that would shape the future of life on Earth in ways that still influence us today. In the harsh interior regions of Pangaea, where temperatures could swing from scorching hot to brutally cold within the span of a single year, reptiles were writing the playbook for survival in extreme environments. These weren't the small lizards and snakes we're familiar with today. We're talking about the early ancestors of dinosaurs, massive creatures that would eventually dominate terrestrial ecosystems for over 160 million years. What made these early reptiles so successful wasn't just their size or their fearsome appearance. It was their revolutionary approach to reproduction and water conservation. Unlike their amphibian ancestors, who had to return to water to lay their eggs, reptiles developed the amniotic egg, essentially a self-contained life support system that allowed their offspring to develop in even the driest environments. These eggs were like tiny spaceships, complete with their own water supply, food storage, and waste management systems. The shell provided protection while allowing gas exchange, and inside Multiple membranes created specialized compartments for the developing embryo. This innovation was so successful that it's still used today by reptiles, birds, and even some mammals. But the reptiles weren't the only ones adapting to Pangaea's harsh conditions. Plant life was undergoing its own revolutionary changes, developing strategies for survival that would fundamentally alter terrestrial ecosystems. The coal-forming swamp forests that had dominated earlier periods were giving way to new types of vegetation better suited to drier conditions. Seed plants were becoming the dominant form of terrestrial vegetation, and for good reason. Unlike the spores produced by earlier plants, seeds were like botanical survival kits, containing everything a young plant needed to establish itself in harsh conditions. Seeds could remain dormant for extended periods, waiting for favorable conditions before germinating. They contained their own food supply and protective coating, allowing plants to colonize areas that had previously been uninhabitable. The diversity of seed plants during this period was absolutely staggering. Early conifers were developing the needle-like leaves and waxy coatings that would allow them to conserve water in dry conditions. Other plants were experimenting with different strategies, developing thick, succulent leaves for water storage or deep root systems that could tap into underground water sources. Meanwhile, in the more hospitable coastal regions, a different kind of evolutionary drama was playing out. The warm, humid conditions near the shores of the Tethys Sea and other water bodies created ideal conditions for the evolution of early mammals, though they wouldn't be recognizable as such to our modern eyes. These proto-mammals were small, furry creatures that looked more like shrews than anything we'd consider a typical mammal today. But they possessed innovations that would eventually allow their descendants to inherit the Earth. They were developing warm-blooded metabolism, allowing them to maintain constant body temperatures regardless of external conditions. They were evolving more sophisticated teeth for processing different types of food, and most importantly, they were developing the complex brain structures that would eventually give rise to intelligence. The geographic isolation created by Pangaea's vast size was driving evolution in fascinating directions. Animals that had once been able to migrate freely across smaller continents now found themselves trapped in specific climate zones by the sheer scale of the supercontinent. This isolation led to rapid diversification as different populations adapted to their local conditions. In the tropical regions near the equator, where monsoon rains brought seasonal moisture, one group of early mammal relatives called cynodonts was thriving. These creatures needed water-rich environments to survive because of their inefficient kidneys, which lost more water during excretion than their reptilian counterparts. The twice-yearly rainfall in their tropical habitat provided just enough moisture to sustain their populations. Further north, in the more temperate regions where rain fell only once a year, a different group of reptile-like animals called procolophonids had carved out their own ecological niche. These creatures were better adapted to drier conditions and could survive on the limited seasonal rainfall that characterized their habitat. This geographic segregation of different animal groups was creating distinct biological provinces across Pangaea, each with its own unique assemblage of species. It was like having multiple worlds within a single continent, each evolving along its own trajectory. The ocean currents surrounding Pangaea were also playing a crucial role in shaping global climate and the evolution of life. The massive size of Panthalassa created circulation patterns unlike anything we see in our modern oceans. Without the complex geography of multiple ocean basins and continents to break up the flow, ocean currents could build up tremendous momentum as they circulated around the supercontinent. These powerful currents transported warm water from equatorial regions toward the poles and brought cold water back toward the equator. But the process was fundamentally different from modern ocean circulation. The lack of major land barriers meant that currents could maintain their temperature and chemical characteristics over much greater distances than they can today. This had profound implications for marine ecosystems. In some regions, the circulation patterns brought nutrient-rich deep waters to the surface, creating areas of incredible biological productivity. In other areas, the currents created vast oceanic deserts where life was scarce. The chemistry of Pangaea's oceans was also dramatically different from what we see today. The reduced amount of shallow shelf seas meant that less carbon dioxide was being absorbed from the atmosphere through the weathering of rocks and the formation of limestone by marine organisms. This led to higher concentrations of carbon dioxide in both the atmosphere and the oceans, contributing to the extreme greenhouse conditions that characterized much of the Pangaea era. These elevated carbon dioxide levels had cascading effects throughout the Earth system. The enhanced greenhouse effect contributed to the extreme continental climate conditions in Pangaea's interior, while the more acidic oceans made it difficult for shell-forming marine organisms to survive. But perhaps the most remarkable aspect of life during the Pangaea era was how it set the stage for one of the most dramatic evolutionary radiations in Earth's history. As harsh as conditions were during the Permian period, they were creating evolutionary pressures that would eventually give rise to the age of dinosaurs. The reptiles that survived the Great Dying weren't just hanging on. They were diversifying rapidly, experimenting with new body plans, new feeding strategies, and new ways of life. Some were becoming larger and more powerful, developing the massive skulls and teeth that would characterize later predatory dinosaurs. Others were exploring herbivory, developing the complex digestive systems needed to process tough plant material. Still others were taking to the air, developing the early flight capabilities that would eventually give rise to pterosaurs and, much later, birds. The evolutionary innovations that emerged during this period of extreme environmental stress would provide the foundation for the spectacular diversity of dinosaurs that would dominate terrestrial ecosystems for the next 160 million years. The plant communities that evolved during the Pangaea era were equally important in setting the stage for future evolutionary developments. The seed plants that adapted to the supercontinent's harsh conditions were developing many of the characteristics that would allow them to coexist with and eventually feed the massive herbivorous dinosaurs of later periods. Conifers were perfecting their needle-like leaves and efficient water transport systems. Early flowering plants were beginning to experiment with the reproductive strategies that would eventually make them the dominant form of terrestrial vegetation. These plants weren't just surviving in Pangaea's challenging conditions. They were laying the groundwork for the complex terrestrial ecosystems that would support the incredible diversity of life that followed. The geological processes that created and sustained Pangaea were also setting the stage for dramatic changes to come. Deep within the Earth's mantle, convection currents were building pressure that would eventually tear the supercontinent apart. Hot plumes of molten rock were rising from the deep mantle, creating zones of weakness in the continental crust that would eventually become the rifts along which Pangaea would split. These deep Earth processes operated on timescales that made the evolution of life seem lightning fast by comparison. The convection currents that would eventually break up Pangaea had been building for tens of millions of years, slowly heating the base of the continental crust and creating the thermal stresses that would eventually cause the supercontinent to fracture. The breakup of Pangaea wouldn't happen all at once. It would be a gradual process spanning tens of millions of years, beginning with the formation of rift valleys and eventually leading to the creation of new ocean basins. But the seeds of this breakup were already being planted during Pangaea's heyday, deep beneath the surface in the churning convection currents of the Earth's mantle. As we look back at this incredible period in Earth's history, it's important to remember that Pangaea wasn't just a curiosity, a strange chapter in our planet's past that has no relevance to our modern world. The processes that created and destroyed this supercontinent are still operating today. The same forces that assembled Pangaea 250 million years ago are continuing to shape our planet, moving continents, creating new ocean basins, and setting the stage for future supercontinents that will form hundreds of millions of years from now. The life forms that evolved during the Pangaea era didn't just disappear when the supercontinent broke apart. Their descendants are all around us today. Every mammal, bird, reptile, and flowering plant on Earth can trace its lineage back to the survivors of this remarkable period, when our planet looked completely different from the world we know today. Understanding Pangaea helps us appreciate just how dynamic our planet really is, how the seemingly solid ground beneath our feet is actually part of a constantly changing system that operates on timescales far beyond human comprehension. It reminds us that the familiar geography of our modern world is just a temporary arrangement, a brief moment in the ongoing story of a planet that has been reshaping itself for billions of years, aping itself for billions of years. The evolutionary innovations happening during Pangaea weren't just random adaptations to harsh conditions. They were laying the foundation for one of the most spectacular chapters in Earth's biological history. As the supercontinent entered its final phase, around 200 million years ago, the stage was being set for changes that would make the previous mass extinctions look like minor disruptions. Deep beneath Pangaea's massive bulk, something extraordinary was brewing. The Earth's mantle, that semi-molten layer of rock beneath the crust, was developing what geologists call superplumes. These weren't just ordinary convection currents. These were massive upwellings of incredibly hot material rising from near the Earth's core, carrying enough thermal energy to literally crack a continent in half. The first signs of what was coming appeared along what would eventually become the eastern seaboard of North America. Long linear valleys began forming, stretching from what is now Nova Scotia all the way down to South Carolina. These weren't just ordinary valleys. They were rift basins, places where the continental crust was beginning to stretch and thin under the enormous stresses building up from below. Picture the Connecticut River Valley, the Culpeper Basin in Virginia, or the Deep River Basin in North Carolina. Today, these look like peaceful, rolling landscapes dotted with farms and small towns. But 200 million years ago, they were active rift zones, places where the Earth itself was beginning to tear apart. These rift valleys filled with sediment eroded from the surrounding highlands, creating thick sequences of red sandstone and mudstone that geologists call the Newark supergroup. But more importantly, they were filling with something else: lava, massive amounts of lava that would eventually create one of the largest volcanic provinces in Earth's history. Around 201 million years ago, at the boundary between the Triassic and Jurassic periods, something unprecedented happened. In what may have been the most concentrated volcanic eruption in Earth's history, an area spanning from what is now Morocco to the Amazon basin began spewing out lava at a rate that defies imagination. This wasn't like the volcanic eruptions we see today. Mount Vesuvius, Mount St. Helens, even the massive eruptions in Iceland. These are barely hiccups compared to what happened at the end of the Triassic. We're talking about flood basalts, sheets of lava that covered areas the size of entire countries and piled up to thicknesses of several miles. Geologists call this the Central Atlantic Magmatic Province, or CAMP for short, and it represents one of the most catastrophic events in Earth's history. The volume of lava produced during this event was so enormous that if you could somehow gather it all together, it would cover the entire continental United States to a depth of over half a mile. But the lava was just part of the story. These eruptions also released massive amounts of gas into the atmosphere. Carbon dioxide, sulfur compounds, and other volcanic gases poured into the sky in quantities that fundamentally altered Earth's climate system. The atmosphere became a toxic soup that made survival incredibly difficult for most life forms. The result was another mass extinction event, though not quite as severe as the Great Dying that had occurred at the end of the Permian. This Triassic-Jurassic extinction event wiped out roughly 76% of all species on Earth, clearing the ecological playing field for the groups that would dominate the next era. And here's where the story gets really interesting. The groups that survived this extinction weren't just random lucky survivors. They were precisely the lineages that would go on to define the Mesozoic era, the age of dinosaurs. The massive volcanic eruptions that destroyed so many ecosystems also created the conditions that allowed dinosaurs to diversify and eventually dominate terrestrial ecosystems. The breakup of Pangaea wasn't happening all at once. It was a gradual process that would continue for the next 150 million years, fundamentally reshaping Earth's geography in ways that are still influencing our planet today. The first major split separated Pangaea into two large landmasses. The northern portion, called Laurasia, included what would become North America, Europe, and Asia. The southern portion, called Gondwana, contained the future South America, Africa, Antarctica, Australia, and India. But even this initial split was incredibly complex. Continents don't just slide apart like pieces of paper. They rotate, they tilt, they fragment into smaller pieces that drift in different directions. Some parts of what we now call North America actually started out attached to Africa. Other pieces that are now part of Europe began their journey attached to what would become North America. The opening of the Atlantic Ocean wasn't just a matter of continents moving apart. It was the birth of an entirely new ocean basin, complete with its own unique circulation patterns, climate effects, and biological communities. As the rift between North America and Africa widened, seawater from the surrounding Panthalassa Ocean began flooding in, creating a narrow seaway that would gradually expand into the mighty Atlantic we know today. This process of ocean formation had profound effects on global climate. The circulation patterns that had characterized Pangaea's climate system were being disrupted and replaced by new patterns that would define Earth's climate for the next 200 million years. The extreme continental climate that had made Pangaea's interior so inhospitable was giving way to more moderate conditions as the continents became smaller and more influenced by maritime climates. The breakup also had dramatic effects on sea level. As the continents separated and new ocean basins formed, the total volume of the ocean basins increased dramatically. This meant that the same amount of water was now spread over a much larger area, causing sea levels to drop significantly compared to the Pangaea era. But here's the counterintuitive part. Even though sea levels were dropping, the amount of shallow marine habitat was actually increasing. The breakup of Pangaea created thousands of miles of new coastline as the continents separated. Islands formed in the new ocean basins. Shallow seas flooded low-lying areas of the continents as they cooled and subsided after rifting. This explosion of shallow marine habitat had exactly the opposite effect of Pangaea's formation. Instead of eliminating marine ecosystems, the breakup created new opportunities for marine life to diversify and thrive. Coral reefs began to flourish in the warm, shallow seas. New types of marine reptiles evolved to take advantage of the expanding ocean environments. On land, the separation of the continents was creating a natural experiment in evolution on a continental scale. Populations of plants and animals that had once been able to interbreed freely across Pangaea were now being separated by growing ocean barriers. This geographic isolation led to rapid evolutionary divergence as different populations adapted to their local conditions. The dinosaurs were the biggest beneficiaries of these changing conditions. As Pangaea broke apart and climates became more moderate and diverse, dinosaurs rapidly diversified into an incredible array of forms. Giant, long-necked sauropods evolved to browse on the tall conifers that flourished in the more humid climates. Armored ankylosaurs developed their defensive adaptations to deal with increasingly sophisticated predators. Theropod dinosaurs experimented with different hunting strategies, some becoming massive apex predators, while others evolved into swift, intelligent pack hunters. But the dinosaurs weren't the only group taking advantage of the changing world. Flowering plants, which had first appeared during the early breakup of Pangaea, were beginning their spectacular radiation that would eventually make them the dominant form of terrestrial vegetation. These early flowers weren't the colourful, showy blooms we're familiar with today. They were small, simple structures, but they represented a revolutionary new approach to reproduction that would change terrestrial ecosystems forever. The coevolution between flowering plants and their pollinators was creating feedback loops that drove both groups to incredible diversity. Insects were evolving new forms and behaviors to take advantage of nectar and pollen resources. Plants were developing increasingly sophisticated strategies to attract pollinators and ensure successful reproduction. The oceans were experiencing their own renaissance as Pangaea broke apart. The restriction of ocean circulation that had contributed to the marine extinctions during Pangaea's formation was being reversed. Cold polar waters could once again circulate into tropical regions, bringing nutrients and oxygen to marine ecosystems. New types of marine reptiles were evolving to fill ecological niches that had been vacant since the Permian extinction. Ichthyosaurs, looking remarkably like modern dolphins despite being reptiles, were becoming the dominant marine predators. Plesiosaurs, with their long necks and powerful flippers, were developing into both fish eaters and mollusk crushers. Marine crocodiles were growing to enormous sizes, some reaching lengths of over 50 feet. The chemistry of the oceans was also changing as Pangaea broke apart. The increased amount of shallow marine habitat meant that more carbon dioxide was being removed from the atmosphere through the weathering of rocks and the formation of limestone by marine organisms. This helped to moderate the extreme greenhouse conditions that had characterized the Pangaea era. But perhaps the most profound change was happening in the deep ocean. As the new ocean basins formed and matured, they developed their own unique circulation patterns. The Atlantic Ocean, in particular, was beginning to develop the circulation system that would eventually become the global conveyor belt of ocean currents that helps regulate Earth's climate today. The Gulf Stream, that massive river of warm water that flows from the Gulf of Mexico up the eastern coast of North America and across to Europe, was beginning to form as the Atlantic widened and deepened. This current system would eventually become crucial for maintaining the relatively mild climates of Western Europe and Eastern North America. In the Pacific, which was shrinking as the Atlantic expanded, different circulation patterns were developing. The Pacific was becoming more isolated from the other ocean basins, developing its own unique characteristics that would persist for hundreds of millions of years. The breakup of Pangaea was also creating new opportunities for the evolution of flight. The fragmented geography of the post-Pangaea world, with its numerous islands and isolated continents, created selective pressures that favored organisms capable of crossing water barriers. Pterosaurs, the first vertebrates to achieve powered flight, were diversifying rapidly during this period. Some species were becoming giants, with wingspans exceeding those of small aircraft. Others were developing specialized feeding strategies, becoming fish eaters, insect catchers, or even filter feeders that strained small organisms from the water like modern flamingos. The success of pterosaurs was paving the way for even more revolutionary developments in vertebrate flight. Deep within the theropod dinosaur family tree, small feathered dinosaurs were beginning to experiment with gliding and eventually powered flight. These early experiments would eventually give rise to birds, though that story was still tens of millions of years in the future. The plant communities that emerged as Pangaea broke apart were unlike anything that had existed before. The combination of more moderate climates, increased atmospheric humidity, and the evolutionary innovations of flowering plants was creating incredibly diverse and productive ecosystems. Forests were becoming more complex, with multiple canopy layers and an incredible diversity of plant forms. Ferns were experiencing their own renaissance, taking advantage of the humid conditions in the undergrowth of these new forests. Conifers were diversifying into forms adapted to different climate zones, from the polar regions to the equator. The soils were also changing as Pangaea broke apart. The extreme weathering conditions that had characterized the supercontinent's arid interior were giving way to more moderate soil formation processes. This led to the development of richer, more fertile soils that could support more diverse plant communities. These changes in terrestrial ecosystems were creating new opportunities for animal life as well. The dinosaurs were just the most visible part of a much broader diversification of terrestrial vertebrates. Early mammals were continuing to evolve, though they remained small and relatively inconspicuous compared to their reptilian contemporaries. Amphibians, which had suffered greatly during the arid conditions of the Pangaea era, were beginning to recover as more humid conditions returned. New types of frogs, salamanders, and caecilians were evolving to take advantage of the expanding aquatic and semi-aquatic habitats. The insect world was experiencing perhaps the most dramatic changes of all. The evolution of flowering plants was creating an explosion of new ecological niches for insects. Butterflies and moths were diversifying rapidly as they co-evolved with their flowering plant hosts. Bees were developing increasingly sophisticated social behaviors and pollination strategies. The ant and termite societies that would eventually become dominant forces in terrestrial ecosystems were beginning to develop their complex social structures. These insects were learning to cultivate fungi, build elaborate nests, and coordinate their activities on a scale that rivaled the achievements of much larger animals. As we trace the breakup of Pangaea through its various stages, we can see how profoundly it changed not just the physical geography of our planet, but the entire trajectory of life's evolution. The harsh, extreme world of the supercontinent gave way to a more diverse, moderate planet that could support an incredible variety of life forms. But the story of continental drift didn't end with the breakup of Pangaea. The same forces that had assembled and then destroyed this supercontinent were continuing to operate, slowly but inexorably reshaping our planet's surface. The continents that emerged from Pangaea's breakup were themselves destined to continue moving, colliding, and separating in an endless dance that continues to this day. The India subcontinent, which had broken away from Gondwana, was beginning its epic journey northward toward Asia, a collision that would eventually create the Himalayan mountain range. Australia was starting its long drift away from Antarctica toward its current position in the South Pacific. Africa was slowly rotating clockwise, setting up the conditions that would eventually close the Tethys Sea and create the Mediterranean. These movements were happening at rates measured in centimeters per year, imperceptible to any individual organism, but accumulating over millions of years into changes that would completely reshape the planet's geography. The world that emerged from Pangaea's breakup was still far from the familiar geography we know today, but it was beginning to take on recognizable features that would persist for hundreds of millions of years. The legacy of Pangaea extends far beyond its direct influence on Earth's geography and climate. The evolutionary innovations that emerged during the supercontinent's existence and breakup continue to shape life on our planet today. Every major group of organisms that dominates modern ecosystems can trace its origins back to the dramatic changes that occurred during this remarkable period in Earth's history. Understanding Pangaea and its breakup gives us crucial insights into how our planet's climate system works, how life responds to environmental change, and how the solid Earth and its living systems interact over geological timescales. It reminds us that our modern world, with its familiar continents and oceans, is just one frame in a much longer movie that has been playing for billions of years and will continue long after our species has vanished from the Earth. The forces that would eventually reshape our planet into its modern form were already stirring beneath the surface as Pangaea entered its twilight years. But before we explore how this massive landmass finally came apart, we need to understand something truly remarkable about the timing. The breakup of Pangaea wasn't just a geological event. It was synchronized with one of the most dramatic biological revolutions in Earth's history, setting the stage for creatures that would capture our imagination like no others. Around 230 million years ago, as the first cracks were beginning to form in Pangaea's continental crust, something extraordinary was happening in the fossil record. Small, bipedal reptiles were starting to appear, creatures that walked upright on their hind legs and possessed skeletal features that would define an entirely new branch of the tree of life. These were the first dinosaurs, and their emergence was no coincidence. The The changing climate conditions as Pangaea began its slow dissolution were creating exactly the environmental pressures that would allow these remarkable creatures to flourish. The extreme continental climate that had characterized the supercontinent's interior was starting to moderate as the landmass began to fragment. Seasonal temperature variations were becoming less severe, and crucially, rainfall patterns were shifting in ways that created new ecological opportunities. But the dinosaurs weren't just lucky beneficiaries of changing conditions. They were evolutionary pioneers, developing innovations that would allow them to dominate terrestrial ecosystems for over 160 million years. Their upright posture wasn't just an anatomical curiosity. It was a revolutionary adaptation that allowed them to move more efficiently than their sprawling reptilian relatives, giving them advantages in both hunting and escaping predators. The early dinosaurs were developing sophisticated respiratory systems that would eventually allow some of their descendants to grow to sizes that seem impossible by modern standards. Their lungs weren't just simple sacs like those of modern reptiles. They were developing the complex air sac systems that we see in modern birds, allowing for much more efficient oxygen extraction and supporting the high metabolic rates needed for active lifestyles. Meanwhile, the plant communities that would feed these emerging giants were undergoing their own revolutionary changes. The seed plants that had adapted to Pangaea's harsh conditions were diversifying into forms that could support much larger herbivores than had ever existed before. Conifers were growing taller and developing more robust trunk structures. Cycads and other seed plants were experimenting with different growth strategies, some becoming massive palm-like trees, while others remained smaller but developed incredibly tough, fibrous leaves. The relationship between these evolving plant communities and the emerging dinosaur fauna was creating feedback loops that would drive both groups to incredible diversity. As herbivorous dinosaurs grew larger, they created selective pressure for plants to develop better defenses, leading to the evolution of spines, toxic compounds, and other protective strategies. In turn, the dinosaurs evolved more sophisticated feeding mechanisms, from the complex dental batteries of duck-billed dinosaurs to the incredibly long necks of sauropods. But the most dramatic changes were happening beneath the surface, in the deep structure of the Earth itself. The mantle plumes that would eventually tear Pangaea apart were building pressure like a geological time bomb. These weren't just ordinary convection currents. They were massive upwellings of superheated rock rising from depths of nearly 3,000 kilometers, carrying enough thermal energy to literally melt their way through the continental crust. The first signs of what was coming appeared around 220 million years ago, when unusual igneous rocks began forming deep within the continental interior. These weren't the typical granites and other rocks you'd expect from normal continental processes. They were alkaline igneous complexes, rocks with chemical signatures that could only form when deep mantle material interacted with the continental crust. Geologists studying these ancient rock formations today can read them like a geological diary, documenting the buildup of thermal stress that was slowly weakening Pangaea from within. The chemical composition of these rocks tells us that the temperature at the base of the continental crust was rising dramatically, approaching the melting point of even the most refractory minerals. As this thermal stress continued to build, the continental crust began to respond in predictable ways. Faults that had been dormant for millions of years started to reactivate. New fracture systems began forming, creating networks of weakness that would eventually become the rifts along which Pangaea would split. The process was incredibly slow by human standards, but geologically speaking, it was happening at breakneck speed. The first major rift system to develop was what geologists call the Central Atlantic Rift, a zone of crustal weakness that stretched from what is now the southeastern United States all the way to northwestern Africa. This wasn't just a single crack in the Earth's surface. It was a complex system of parallel faults, grabens, and horsts that extended for thousands of kilometers. Within these rift valleys, conditions were unlike anything that had existed on Pangaea's surface before. The stretching and thinning of the continental crust created topographic depressions that became natural collection points for water and sediment. Lakes formed in these basins, some of them enormous by modern standards, creating aquatic ecosystems in the heart of what had been arid continental interior. These Rift Valley lakes became evolutionary laboratories where aquatic life could experiment with new forms and strategies. Fish populations that had been restricted to coastal environments suddenly had access to vast new freshwater habitats. Some species adapted to the unique chemical conditions of these inland lakes, which were often highly alkaline due to the volcanic activity associated with the rifting process. The sedimentary rocks that accumulated in these ancient lake basins have preserved some of the most spectacular fossils from this crucial period in Earth's history. Perfectly preserved fish, early dinosaurs, and even delicate plant fossils tell the story of ecosystems that were adapting rapidly to the changing conditions as Pangaea began its transformation. But the lakes were just the beginning. As the rifting process intensified, something much more dramatic was building toward a crescendo that would change the face of the Earth forever. Deep within the mantle, the superplumes that had been slowly heating the base of the continental crust were approaching a critical threshold. The pressure and temperature conditions were reaching the point where massive volumes of rock would begin to melt simultaneously. Around 201 million years ago, this geological powder keg finally exploded. The Central Atlantic Magmatic Province, or CAMP, represents one of the largest volcanic events in Earth's recorded history. Over a period of just a few 100,000 years, an area roughly the size of the United States was covered with flood basalts, sheets of lava that in some places reached thicknesses of several kilometers. The scale of this volcanic catastrophe is almost impossible to comprehend. The volume of lava produced during the CAMP eruptions was roughly 4 million cubic kilometers, enough to bury the entire state of Texas under a mile of molten rock. But the lava was just the most visible part of a much larger geological upheaval that was tearing Pangaea apart along predetermined lines of weakness. The eruptions weren't confined to a single location. They occurred simultaneously across an area spanning from Morocco to Nova Scotia, from the Amazon basin to the mountains of Europe. This synchronized volcanic activity was the direct result of the mantle superplume finally breaking through to the surface, releasing the enormous thermal energy that had been building up for tens of millions of years. The environmental consequences of these eruptions were catastrophic on a global scale. The massive volumes of volcanic gas released into the atmosphere fundamentally altered Earth's climate system. Carbon dioxide concentrations spiked to levels not seen since the early days of Pangaea's formation. Sulfur compounds created acid rain that fell across vast regions. Toxic gases made the air itself lethal to most forms of life. But perhaps even more devastating were the effects on the oceans. The volcanic gases didn't just stay in the atmosphere. They dissolved into seawater, creating conditions that were toxic to most marine life. Ocean acidity levels spiked, making it impossible for shell-forming organisms to extract the calcium carbonate they needed from seawater. Oxygen levels plummeted as the warmer, more acidic waters could hold less dissolved gas. The result was the Triassic-Jurassic extinction event, a biological catastrophe that eliminated roughly 3/4 of all species on Earth. But unlike the great dying that had occurred at the end of the Permian, this extinction event was highly selective. The groups that survived weren't just random lucky survivors. They were precisely the lineages that were best adapted to the new world that was emerging as Pangaea broke apart. The dinosaurs were among the biggest winners in this biological lottery. The environmental changes that were devastating to many other groups actually created ideal conditions for dinosaur diversification. The fragmentation of Pangaea was creating a more geographically complex world with a greater variety of habitats and climates. This diversity of environments provided opportunities for dinosaurs to evolve into an incredible array of forms, from tiny bird-like species to giants that weighed more than modern elephants. The volcanic activity that was tearing Pangaea apart was also creating new types of habitats that hadn't existed before. Volcanic islands were forming in the growing ocean basins, providing stepping stones for the dispersal of organisms between the separating continents. These islands became evolutionary laboratories where isolated populations could evolve in new directions, free from competition with their mainland relatives. The chemical weathering of the fresh volcanic rocks was creating extremely fertile soils that could support much more productive plant communities than had been possible on the ancient weathered soils of Pangaea's interior. These volcanic soils were rich in nutrients that had been locked up in the deep earth for billions of years, and their availability at the surface created opportunities for explosive plant growth and diversification. The changing ocean circulation patterns as Pangaea broke apart were also having profound effects on global climate. The formation of new ocean basins was disrupting the circulation patterns that had characterized the Pangaea era and replacing them with more complex systems that could transport heat and moisture more efficiently around the planet. The Gulf Stream system, which today helps maintain the relatively mild climate of Western Europe, was beginning to form as the North Atlantic Ocean opened between North America and Europe. This massive current system transports roughly 30 times more water than all the world's rivers combined, and its development was crucial for establishing the climate patterns that would characterize the post-Pangaea world. In the Pacific Ocean, which was shrinking as the Atlantic expanded, different circulation patterns were developing. The Pacific was becoming more thermally isolated from the other ocean basins, developing its own unique characteristics that included some of the most extreme deep-water environments on Earth. These changing ocean conditions were creating new opportunities for marine life to diversify and evolve. The restriction of ocean circulation that had contributed to the marine extinctions during Pangaea's formation was being reversed. Cold, oxygen-rich polar waters could once again circulate into tropical regions, bringing nutrients and supporting more diverse marine ecosystems. New types of marine reptiles were evolving to fill ecological niches that had been vacant since the Permian extinction. Ichthyosaurs, despite being reptiles, were developing body forms that were remarkably similar to modern dolphins and whales. Their streamlined bodies, powerful tails, and sophisticated echolocation abilities made them incredibly effective marine predators. Plesiosaurs were taking a different evolutionary approach, developing long necks and powerful flippers that made them highly maneuverable swimmers. Some species became specialists at catching fish, while others evolved massive heads and powerful jaws for crushing shellfish and other hard-shelled prey. Marine crocodiles were also experiencing a renaissance during this period, growing to sizes that dwarfed their modern relatives. Some species reached lengths of over 50 feet and possessed adaptations for life in the open ocean, including salt-excreting glands and flippers instead of legs. But perhaps the most remarkable aspect of the post-Pangaea marine ecosystems was their incredible diversity and productivity. The expansion of shallow marine habitats as the continents separated created opportunities for coral reefs to flourish on a scale that hadn't been seen since before the Great Dying. These reef ecosystems became centers of marine biodiversity, supporting complex food webs that included everything from tiny plankton to massive marine reptiles. The breakup of Pangaea was also having profound effects on the evolution of flight. The fragmented geography of the post-Pangaea world, with its numerous islands and water barriers, created selective pressures that favored organisms capable of crossing these obstacles. Pterosaurs, the first vertebrates to achieve powered flight, were diversifying rapidly during this period. Some species were becoming specialized for different feeding strategies, from fish-eating forms with long, narrow beaks to filter feeders with bizarre comb-like structures for straining small organisms from the water. The largest pterosaurs were truly spectacular creatures, with wingspans that exceeded those of small aircraft. These giants were able to soar for hours without flapping their wings, using thermal updrafts to stay aloft while searching for food over vast areas of ocean and land. The success of pterosaurs was demonstrating the incredible advantages of powered flight in the post-Pangaea world. The ability to cross water barriers and access resources that were unavailable to terrestrial organisms was providing flying creatures with evolutionary opportunities that would persist for hundreds of millions of years. Deep within the theropod dinosaur lineage, small feathered species were beginning their own experiments with aerial locomotion. These early attempts at flight were still crude compared to the sophisticated flying abilities of pterosaurs, but they represented the first steps toward what would eventually become one of the most successful groups of flying animals in Earth's history. The plant communities that emerged as Pangaea broke apart were creating the foundation for terrestrial ecosystems of unprecedented complexity and diversity. The more moderate climates and increased atmospheric humidity were allowing plants to explore new evolutionary strategies that hadn't been possible during the harsh conditions of the supercontinent era. Flowering plants, which had first appeared during the early stages of Pangaea's breakup, were beginning their spectacular radiation that would eventually make them the dominant form of terrestrial vegetation. These early flowers were small and inconspicuous compared to modern blooms, but they represented a revolutionary new approach to reproduction that would change terrestrial ecosystems forever. The coevolution between flowering plants and their insect pollinators was creating feedback loops that drove both groups to incredible diversity. Insects were evolving new forms and behaviors to take advantage of nectar and pollen resources, while plants were developing increasingly sophisticated strategies to attract pollinators and ensure successful reproduction. The forests that developed during this period were unlike anything that had existed before on Earth. Multiple canopy layers created complex three-dimensional habitats that could support incredible diversity of both plant and animal life. Epiphytes, plants that grow on other plants without parasitizing them, were beginning to colonize the upper reaches of these forests, creating aerial gardens that added yet another layer of complexity to these ecosystems. The soils beneath these forests were also undergoing dramatic changes. The combination of more moderate climates, increased precipitation, and the input of organic matter from the diverse plant communities was creating rich, fertile soils that could support much more productive ecosystems than had been possible during the Pangaea era. These changes in soil chemistry were having cascading effects throughout terrestrial food webs. The increased availability of nutrients was supporting larger populations of decomposer organisms, which in turn created more complex soil ecosystems. These soil communities were becoming increasingly important for nutrient cycling and plant growth, creating positive feedback loops that further enhanced ecosystem productivity. The diversification of terrestrial ecosystems was creating new opportunities for animal evolution as well. The dinosaurs were just the most visible part of a much broader radiation of terrestrial vertebrates that was taking advantage of the expanding variety of habitats and food sources. Early mammals were continuing their own evolutionary experiments, though they remained relatively small and inconspicuous compared to their reptilian contemporaries. However, they were developing increasingly sophisticated adaptations that would eventually allow their descendants to inherit the Earth. The mammalian innovations that emerged during this period included more efficient metabolisms that allowed for sustained activity levels, more sophisticated sensory systems for navigating complex environments, and increasingly complex social behaviors that enhanced survival in diverse habitats. Amphibians, which had suffered greatly during the arid conditions of the Pangaea era, were experiencing their own renaissance as more humid conditions returned. New types of frogs, salamanders, and caecilians were evolving to take advantage of the expanding aquatic and semi-aquatic habitats created by the changing climate and geography. The insect world was perhaps experiencing the most dramatic changes of all. The evolution of flowering plants was creating an explosion of new ecological niches that insects were quick to exploit. The relationships between insects and plants were becoming increasingly specialized, leading to coevolutionary arms races that drove both groups to ever greater diversity. Butterflies and moths were diversifying rapidly as they co-evolved with their flowering plant hosts. The development of proboscis tongues allowed them to access nectar from increasingly deep flowers, while plants evolved longer corolla tubes to ensure that only their preferred pollinators could reach their rewards. Bees were developing increasingly sophisticated social behaviors and pollination strategies. The evolution of eusociality in some bee lineages was creating superorganisms that could coordinate their activities on a scale that rivaled the achievements of much larger animals. Ants were also beginning to develop the complex social structures that would eventually make them one of the most successful groups of organisms on Earth. These insects were learning to cultivate fungi, build elaborate nests, and coordinate their activities in ways that allowed them to dominate many terrestrial ecosystems. As we trace the breakup of Pangaea through its various stages, we can see how profoundly it changed not just the physical geography of our planet, but the entire trajectory of life's evolution. The harsh, extreme world of the supercontinent was giving way to a more diverse, moderate planet that could support an incredible variety of life forms. The continental fragments that emerged from Pangaea's breakup were themselves beginning new journeys that would continue for hundreds of millions of years. The forces that had assembled and then destroyed this supercontinent were still operating, slowly but inexorably, continuing to reshape our planet's surface in ways that would eventually create the familiar world we know today. The movements of these newly separated continental masses weren't random drifts across the ocean. They were following predictable paths dictated by the same deep mantle convection currents that had torn Pangaea apart in the first place. Each continental fragment was riding on its own tectonic plate, carried along by forces operating thousands of miles beneath the surface. India, which had broken away from the southern supercontinent of Gondwana, was beginning one of the most epic journeys in geological history. This wasn't just a continent slowly drifting northward. It was a continental bullet train moving at speeds that were extraordinary by geological standards, sometimes covering as much as 20 centimeters per year. The Indian subcontinent was ploughing through the ancient Tethys Ocean like an unstoppable force, leaving a trail of geological evidence that scientists can still read today. As it moved northward, it was consuming oceanic crust at a rate that would make modern subduction zones look leisurely by comparison. The ocean floor ahead of it was being dragged down into the mantle and recycled, while volcanic island chains marked its passage like breadcrumbs in a geological fairy tale. But India's journey was far from over. Ahead lay the massive bulk of Asia, and when these two continental masses eventually collided around 50 million years ago, the impact would create the highest mountain range on Earth. The Himalayas weren't just going to be tall mountains. They would become a geological monument to the incredible forces unleashed when continents collide at full speed. Meanwhile, Australia was beginning its own remarkable odyssey. Breaking away from Antarctica around 100 million years ago, it started drifting northward toward its eventual rendezvous with Southeast Asia. This journey would take Australia through a variety of climate zones, from its original position near the South Pole to its current location straddling the equator. The separation of Australia and Antarctica had profound consequences for global climate. These two continents had been joined for hundreds of millions of years, and their separation opened up the Southern Ocean, allowing the development of the circumpolar current that still encircles Antarctica today. This current system would eventually become crucial for maintaining Antarctica's ice sheets and regulating global ocean circulation. Africa was undergoing its own complex dance of rotation and drift. The continent was slowly rotating clockwise while simultaneously moving northward, setting up conditions that would eventually close the Tethys Sea and create the Mediterranean. This wasn't a simple collision. Africa's movement was compressing the ocean basin between it and Europe, creating the geological conditions that would eventually give rise to the Alps, the Pyrenees, and other major European mountain ranges. The closure of the Tethys Sea would have consequences that extended far beyond mountain building. This ancient ocean had been a major pathway for marine circulation between the Atlantic and Indian Oceans. As it gradually closed, global ocean circulation patterns would be forced to reorganize, contributing to long-term climate changes that are still influencing our planet today. South America was also on the move, but its journey was more complex than simple drift. The continent was rotating as it moved westward, driven by the expansion of the South Atlantic Ocean. This rotation was causing different parts of South America to experience different rates of movement, creating internal stresses that contributed to the formation of the Andes Mountains. The Andes weren't just forming from the collision between South America and the oceanic Nazca Plate. They were also being shaped by the rotational forces acting on the continent as it moved away from Africa. This combination of collision and rotation was creating one of the longest and most geologically complex mountain ranges on Earth. North America's journey was equally fascinating. The continent was rotating counterclockwise as it moved away from Europe and Africa, opening up the North Atlantic Ocean. But this wasn't just a simple separation. Parts of what we now consider North America had actually started out attached to other continents and had been transferred during the breakup process. The Avalon terrain, which includes parts of New England and the maritime provinces of Canada, had originally been part of the northern coast of Gondwana. During the complex process of Pangaea's assembly and breakup, this piece of ancient Africa had been transferred to North America, carrying with it distinctive rocks and fossils that tell the story of its intercontinental journey. These continental movements were having profound effects on ocean circulation patterns. As the Atlantic Ocean continued to expand and deepen, it was developing the complex current systems that would eventually become crucial for regulating global climate. The formation of deep water masses in the North Atlantic was creating a global conveyor belt of ocean circulation that transported heat and nutrients around the planet. The Pacific Ocean, meanwhile, was shrinking as the Atlantic expanded. But this wasn't just a matter of changing size. The Pacific was becoming more isolated from the other ocean basins, developing its own unique characteristics that included some of the deepest and most chemically distinct water masses on Earth. The Ring of Fire, that zone of intense volcanic and seismic activity that encircles the Pacific, was beginning to take shape as the oceanic plates in the Pacific were increasingly surrounded by converging continental margins. This geological reorganization was creating the conditions for some of the most dramatic volcanic eruptions and earthquakes in Earth's history. The changing geography was also having profound effects on atmospheric circulation patterns. The distribution of continents and oceans plays a crucial role in determining how heat and moisture are transported around the planet, and the post-Pangaea world was developing circulation patterns that were fundamentally different from those of the supercontinent era. The monsoon systems that had characterized Pangaea were breaking down and being replaced by more complex regional climate patterns. The fragmentation of the supercontinent was creating more varied topography, with mountain ranges and ocean basins that could generate their own local weather patterns. These changing atmospheric conditions were creating new opportunities for the evolution of life. The dinosaurs were taking full advantage of the increasingly diverse range of climates and habitats. Some species were adapting to the hot, humid conditions of the expanding tropical regions. Others were evolving to thrive in the more temperate climates that were developing at higher latitudes. The giant sauropod dinosaurs were becoming increasingly common during this period, and their success was directly linked to the changing plant communities. The conifers and other seed plants that dominated post-Pangaea forests were growing to enormous sizes, creating vast quantities of food at heights that only the longest-necked dinosaurs could reach. These plant-eating giants weren't just passive consumers of vegetation, they were ecosystem engineers, their feeding activities shaping the structure and composition of the forests they inhabited. Their ability to browse at heights of 30 feet or more was creating a kind of vertical zonation in forest communities, with different plant species adapted to different levels of the canopy. The predatory dinosaurs were also diversifying rapidly, developing increasingly sophisticated hunting strategies to deal with their massive prey. Some species were evolving pack hunting behaviors, working together to bring down prey much larger than any individual could handle alone. Others were becoming solitary apex predators, growing to sizes that would make modern large carnivores look like house cats. But perhaps the most remarkable evolutionary development was happening among the smaller theropod dinosaurs. Some lineages were developing increasingly bird-like characteristics, including hollow bones for reduced weight, sophisticated respiratory systems for efficient oxygen use, and most importantly, feathers for insulation and display. The evolution of feathers represents one of the most significant innovations in the history of life. These structures weren't originally developed for flight. They first appeared as insulation, helping small dinosaurs maintain stable body temperatures in the increasingly variable climates of the post-Pangea world. But once feathers existed, they could be modified for other purposes, including display and eventually flight. The early experiments with powered flight were crude compared to the sophisticated flying abilities of pterosaurs, but they represented the beginning of what would eventually become one of the most successful groups of flying animals in Earth's history. The ancestors of modern birds were taking their first tentative steps toward conquering the skies. Marine ecosystems were also experiencing unprecedented diversification during this period. The expansion of shallow marine habitats as the continents separated was creating opportunities for coral reefs to develop on a scale that hadn't been seen for hundreds of millions of years. These reef ecosystems were becoming incredibly complex, supporting food webs that included everything from microscopic plankton to massive marine reptiles. The diversity of marine life during this period was staggering, with new species evolving at rates that rival the most dramatic adaptive radiations in Earth's history. The ammonites, those spiral-shelled relatives of modern squid and octopi, were experiencing their own golden age during this period. These cephalopods had survived the Triassic-Jurassic extinction and were diversifying into an incredible array of forms. Some species developed shells with complex internal chambers for buoyancy control. Others evolved shells with elaborate spines and ridges that may have served as protection against predators. The success of ammonites was contributing to the evolution of their predators as well. Marine reptiles were developing increasingly sophisticated strategies for cracking open ammonite shells, leading to evolutionary arms races that drove both groups to greater complexity and diversity. Belemnites, the bullet-shaped relatives of modern squid, were also thriving during this period. These creatures were developing sophisticated jet propulsion systems that allowed them to move through the water with remarkable speed and agility. Their fossilized remains are found in marine rocks around the world, testament to their success in the post-Pangea oceans. The microscopic marine life was equally important in shaping these ecosystems. Coccolithophores, tiny planktonic algae that produce intricate calcium carbonate plates, were becoming increasingly abundant. These organisms were not only important primary producers in marine food webs, but their calcium carbonate shells were also contributing to the formation of some of the most distinctive rock formations of this period. The White Cliffs of Dover, those iconic chalk formations along the English Channel, are composed almost entirely of the fossilized remains of these tiny marine organisms. The thickness of these chalk deposits, sometimes hundreds of meters deep, gives us some sense of just how productive marine ecosystems were during this period. The changing chemistry of the oceans was also having important effects on the carbon cycle. The increased area of shallow marine environments was providing more opportunities for the burial of organic carbon in marine sediments. This was helping to draw down atmospheric carbon dioxide levels, contributing to the gradual cooling that would eventually lead to the development of polar ice caps. But the most dramatic changes were still happening on land. The flowering plants that had first appeared during the early breakup of Pangaea were beginning their spectacular radiation that would eventually make them the dominant form of terrestrial vegetation. The early angiosperms, as flowering plants are scientifically known, were small, herbaceous plants that looked nothing like the spectacular flowers we're familiar with today, but they possessed a revolutionary reproductive strategy that gave them enormous advantages over their competitors. Unlike the conifers and other gymnosperms that dominated earlier plant communities, flowering plants could reproduce much more rapidly and efficiently. Their flowers allowed for more precise control over pollination, while their fruits provided better protection and dispersal for their seeds. The coevolution between flowering plants and their insect pollinators was creating feedback loops that drove both groups to incredible diversity. Insects were evolving new forms and behaviors to take advantage of nectar and pollen resources, while plants were developing increasingly sophisticated strategies to attract their preferred pollinators. Beetles were among the first insects to take advantage of flowering plants, and many of the earliest flowers were probably pollinated by these generalist feeders. But as the relationship between plants and pollinators became more specialized, more sophisticated partnerships began to develop. Butterflies and moths were evolving longer proboscises to reach nectar in increasingly deep flowers. Bees were developing specialized structures for collecting and transporting pollen. Flies were adapting to pollinate flowers with specific scents and colors that matched their sensory preferences. This diversification of plant-pollinator relationships was creating incredible botanical diversity. Different lineages of flowering plants were experimenting with different strategies for attracting pollinators, leading to the evolution of flowers with every imaginable combination of size, shape, color, and scent. Some plants were developing massive, showy flowers designed to attract large, strong pollinators. Others were evolving tiny, inconspicuous flowers that relied on wind or water for pollination. Still others were developing complex flower structures that could only be pollinated by insects with very specific behaviors or anatomical features. The fruits that these plants produced were equally diverse. Some species developed fleshy, colorful fruits designed to attract animals that would eat them and disperse their seeds. Others evolved dry fruits with wings or other structures for wind dispersal. Still others developed fruits with hooks or spines that would attach to passing animals. This explosion of angiosperm diversity was having cascading effects throughout terrestrial ecosystems. The new types of fruits and seeds were providing food resources for animals that hadn't existed before. The more efficient reproduction of flowering plants was allowing them to colonize new habitats and outcompete established plant communities. The insects that were co-evolving with flowering plants were also diversifying rapidly. The number of insect species was exploding as different lineages adapted to feed on different plant species or plant parts. This diversification of insects was creating new food webs that supported higher levels of biodiversity than had existed before. Birds, which were just beginning their own evolutionary radiation, were finding abundant food in the form of insects, fruits, and seeds produced by the diversifying angiosperm communities. The evolution of different beak shapes and sizes allowed different bird species to specialize on different types of food, reducing competition and allowing more species to coexist. The mammals, though still relatively small and inconspicuous compared to the dinosaurs, were also benefiting from the diversification of flowering plants. New types of fruits and seeds provided concentrated sources of energy that could support higher metabolic rates. Some mammal lineages were beginning to specialize on particular types of plant foods, leading to the evolution of different dental patterns and digestive systems. The changing plant communities were also affecting soil development and nutrient cycling. The roots of flowering plants often formed different types of associations with soil microorganisms than those of conifers and other earlier plant groups. These new plant microbe partnerships were creating more efficient systems for nutrient uptake and cycling, further enhancing ecosystem productivity. The leaf litter produced by deciduous flowering plants was also different in composition from the needles and other debris produced by conifers. This was creating new opportunities for decomposer organisms and contributing to the development of richer, more fertile soils. All of these changes were happening against the backdrop of continued continental drift and geological activity. The forces that had broken up Pangaea were still operating, continuing to reshape the planet's surface in ways that would create new opportunities for evolution. Volcanic activity was creating new islands and land bridges that served as stepping stones for the dispersal of organisms between continents. Mountain building was creating new climate zones and habitats. The opening and closing of ocean basins was altering circulation patterns and affecting regional climates. The world that was emerging from Pangaea's breakup was becoming increasingly complex and diverse. The simple, extreme conditions that had characterized the supercontinent era were giving way to a mosaic of different environments, each with its own unique opportunities and challenges for life. This environmental complexity was driving evolutionary innovation at an unprecedented pace. The number of species on Earth was increasing rapidly as organisms adapted to fill the expanding variety of ecological niches. New types of interactions between species were evolving, creating more complex food webs and ecological relationships. The foundations were being laid for the modern world's incredible biodiversity. The major groups of organisms that dominate today's ecosystems were taking shape during this crucial period when the rigid constraints of the supercontinent world were giving way to the dynamic, ever-changing planet we know today. The transformation wasn't happening in isolation. Each change was triggering cascades of other changes, creating a web of interconnected processes that would reshape life on Earth in ways that are still unfolding today, as the continents continued their slow-motion dance across the planet's surface. They were carrying with them entire ecosystems that would be forced to adapt to radically new conditions. Australia's journey northward from Antarctica provides one of the most remarkable examples of how continental drift can drive evolution. When these two landmasses were still connected, they shared similar cool, temperate climates and similar flora and fauna. But as Australia began its migration toward the equator, it was essentially taking an entire continent's worth of organisms on a climate journey that would last over 100 million years. The plants and animals that rode along on this continental arc were forced to adapt to increasingly warm and dry conditions as Australia moved through different climate zones. Some lineages went extinct when they couldn't keep pace with the changing conditions. Others evolved remarkable adaptations that allowed them to thrive in their new environments. The eucalyptus trees that now dominate much of Australia's landscape are direct descendants of plants that began this journey in cool, moist forests near the South Pole. Over millions of years, they evolved the waxy leaves, efficient water storage systems, and fire-resistant bark that allow them to survive in some of the world's most challenging environments. The marsupials that make Australia famous today tell a similar story. These pouched mammals were once found on all the southern continents, but as Australia became isolated from the rest of the world, they evolved in splendid isolation. Without competition from the placental mammals that were diversifying on other continents, Australian marsupials radiated into ecological niches that were filled by very different types of animals elsewhere. The result was the evolution of marsupial equivalents of wolves, bears, cats, mice, and even something resembling a saber-toothed tiger. Each of these represented an independent evolutionary experiment in how to make a living in Australia's changing environments. But Australia's story was just one thread in a much larger tapestry of evolutionary change. Across the fragmenting remains of Pangaea, similar processes were playing out as different continental pieces carried their biological cargo toward new destinies. The separation of South America from Africa, around 130 million years ago, created another natural laboratory for evolutionary experimentation. These two continents had shared similar tropical climates and ecosystems when they were joined, but their separation led to the independent evolution of remarkably different biological communities. In South America, the mammals that had survived the Triassic-Jurassic extinction began evolving into forms that had no equivalent anywhere else on Earth. Giant ground sloths the size of elephants browsed on the increasingly diverse plant communities. Armadillos grew to the size of automobiles, their bony shells providing protection from predators that were equally oversized. The predatory mammals that evolved in South America were unlike anything seen elsewhere. Terror birds, flightless giants with massive beaks and powerful legs, became the dominant predators in many ecosystems. Some species grew to heights of over 10 feet and possessed beaks that could crush the bones of their prey with ease. Meanwhile, in Africa, a completely different set of evolutionary experiments was unfolding. The mammals that remained on this continent after the separation were evolving along different trajectories, eventually giving rise to the elephants, rhinos, hippos, and big cats that we associate with African wildlife today. The differences between South American and African mammal communities became even more pronounced over time, providing compelling evidence for the reality of continental drift. When scientists first began studying the fossil records of these continents, they found that despite their current geographic separation, the ancient fossils were remarkably similar. But as they traced the evolutionary history forward in time, the similarities disappeared and were replaced by increasingly different assemblages of species. This pattern of increasing divergence over time provided some of the strongest evidence for Wegener's theory of continental drift long before the mechanisms of plate tectonics were understood. The biological evidence was telling the same story as the geological evidence. These continents had once been joined and had subsequently drifted apart. The breakup of Gondwana, the southern portion of Pangaea, was creating similar patterns of evolutionary divergence across multiple continents. Madagascar, that large island off the eastern coast of Africa, broke away from the mainland around 160 million years ago and has been evolving in isolation ever since. The result is one of the world's most unique biological communities. Lemurs, which went extinct on the African mainland due to competition with other primates, survived and diversified on Madagascar into an incredible array of forms. Some species became as large as gorillas, while others remained tiny and nocturnal. Some developed specialized diets of leaves, others focused on fruits, and still others became omnivores that would eat almost anything. The plants of Madagascar show similar patterns of unique evolution. The island is home to thousands of species that exist nowhere else on Earth, including the bizarre baobab trees with their massive trunks and tiny crowns, and the octopus trees with their thick, succulent branches that look more like tentacles than typical tree limbs. But perhaps the most remarkable aspect of Madagascar's biological evolution is how it demonstrates the power of isolation to drive innovation. Without the competitive pressures and predation risks that existed on the larger continents, Madagascar's organisms were free to evolve in directions that would have been impossible elsewhere. The carnivorous plants that evolved on the island developed some of the most sophisticated trapping mechanisms known to science. The pitcher plants of Madagascar don't just passively wait for insects to fall into their traps. Some species have evolved active mechanisms that can snap shut on their prey with remarkable speed and precision. These evolutionary innovations weren't just curiosities. They were solutions to the unique challenges posed by life on an isolated island with limited resources and unusual ecological pressures. The same processes were playing out on countless other islands and continental fragments as Pangaea's breakup created an increasingly complex global geography. The formation of the Atlantic Ocean wasn't just creating new barriers between continents, it was also creating new opportunities for marine life to diversify and spread. As the ocean basin widened and deepened, it developed its own unique circulation patterns and environmental conditions that supported the evolution of distinctly Atlantic marine communities. The Mid-Atlantic Ridge, that underwater mountain range that marks where new oceanic crust is still being formed today, became a kind of evolutionary highway for deep-sea organisms. The hydrothermal vents along the ridge created unique chemical environments that supported communities of organisms, unlike anything found elsewhere on Earth. These vent communities were based not on photosynthesis, like most ecosystems, but on chemosynthesis, the ability of certain bacteria to derive energy from chemical reactions involving hydrogen sulfide and other compounds. The discovery of these communities in modern times revolutionized our understanding of the limits of life, but they had been evolving and diversifying for hundreds of millions of years. The organisms that live around hydrothermal vents had to solve problems that no other life forms had ever faced. How do you survive in water that's hot enough to melt lead? How do you find food in the complete darkness of the deep ocean floor? How do you reproduce when your habitat might disappear overnight if the geological activity that creates the vents shifts to a new location? The solutions that evolved were as bizarre as they were ingenious. Giant tube worms with no digestive systems relied entirely on symbiotic bacteria living in their tissues to provide nutrition. Eyeless shrimp developed sophisticated chemical sensors that allowed them to navigate in complete darkness. Bacteria evolved heat-resistant proteins that remained functional at temperatures that would denature the proteins of most other organisms. These deep-sea communities were just one example of how the changing geology of the post-Pangea world was creating new environments that life could colonize and adapt to. The increasing complexity of Earth's geography was providing an ever-expanding array of ecological niches that organisms could exploit. On land, the continued fragmentation and movement of continents was creating equally diverse opportunities for evolutionary innovation. The collision between India and Asia, which began around 50 million years ago, created not just the Himalayas, but also a series of smaller mountain ranges and high plateaus that provided habitats unlike anything that had existed before. The Tibetan Plateau, sometimes called the roof of the world, became a high-altitude laboratory for evolution. The combination of extreme elevation, intense solar radiation, and harsh climate conditions created selective pressures that drove the evolution of remarkable adaptations in both plants and animals. The plants that colonized the plateau had to solve the problem of surviving at altitudes where the air is thin, the temperatures are extreme, and the growing season is incredibly short. Many species evolved compact, cushion-like growth forms that helped them conserve heat and resist the constant winds. Others developed deep taproot systems that could access water and nutrients from far below the surface. The animals that adapted to life on the plateau faced equally challenging conditions. The low oxygen levels at high altitude required modifications to their respiratory and circulatory systems that allowed them to extract oxygen more efficiently from the thin air. Many species evolved thicker fur or feathers for insulation against the cold, and behavioral adaptations for surviving the long, harsh winters. But the Himalayan uplift had effects that extended far beyond the immediate region of the collision. The massive mountain range began to alter atmospheric circulation patterns across much of Asia, creating the monsoon systems that still dominate the climate of the Indian subcontinent and Southeast Asia today. The monsoons brought seasonal rainfall to vast areas that had previously been much drier, allowing for the development of new types of ecosystems and the evolution of organisms adapted to strongly seasonal environments. The timing of reproduction, migration, and other critical life events became synchronized with the predictable patterns of wet and dry seasons. These seasonal environments also favored the evolution of deciduous plants that could shut down their metabolic processes during the dry season and then rapidly resume growth when the rains returned. This strategy allowed plants to thrive in environments where year-round growth would be impossible due to water limitations. The seasonal leaf drop from deciduous forests created new types of soil environments that supported different communities of decomposer organisms. The annual cycle of leaf fall and decomposition created pulses of nutrient availability that many organisms learned to exploit. The formation of other major mountain ranges during this period was having similar effects on regional climates and ecosystems. The Andes Mountains, created by the collision between South America and the oceanic Nazca Plate, were generating their own complex patterns of rainfall and temperature that created a vertical zonation of ecosystems from tropical lowlands to alpine tundra. This vertical diversity allowed South America to support an incredible variety of life forms within relatively small geographic areas. A journey from the Amazon basin to the peaks of the Andes could take you through more different types of ecosystems than a trip across an entire continent in other parts of the world. The organisms that lived along these elevational gradients had to cope with dramatically different conditions over relatively short distances. Many species evolved into chains of closely related populations, adapted to different elevations, creating natural laboratories for studying how evolution responds to environmental gradients. The birds that lived along these mountain slopes provide some of the best examples of adaptive radiation in response to elevation. Different species evolved specialized beaks, wing shapes, and metabolic systems that allowed them to thrive at different altitudes. Some became high-altitude specialists with enlarged hearts and lungs for coping with thin air. Others remained lowland species, but developed the ability to migrate seasonally between different elevations as food resources changed. The continuing breakup of Pangaea was also affecting ocean circulation in ways that would have profound consequences for global climate. The opening of seaways between previously connected continents allowed new patterns of water flow that could transport heat and nutrients more efficiently around the planet. The opening of the Drake Passage between South America and Antarctica, which occurred around 35 million years ago, was particularly important. This narrow seaway allowed the development of the Antarctic Circumpolar Current, a massive current system that completely encircles Antarctica and effectively isolates it from warmer waters to the north. The formation of this current system was crucial for the development of Antarctica's ice sheets. By preventing warm water from reaching the continent, the circumpolar current allowed Antarctica to become much colder than it would have been otherwise. The result was the formation of continental ice sheets that have persisted for millions of years and continue to play a crucial role in regulating global climate today. The ice sheets themselves became new environments that life had to adapt to. The few organisms that managed to survive in Antarctica's increasingly harsh conditions evolved remarkable adaptations for coping with extreme cold, intense seasonal variations in daylight, and the constant presence of ice and snow. Antarctic fish evolved antifreeze proteins that prevent ice crystals from forming in their body fluids. Seals and penguins developed thick layers of insulation and sophisticated behavioral strategies for conserving heat. Even the microorganisms that live in Antarctic soils evolved specialized biochemical pathways that remain functional at temperatures well below freezing. But the effects of Antarctica's isolation extended far beyond the continent itself. The formation of the ice sheets locked up vast amounts of water that had previously been part of the ocean system. This caused global sea levels to drop, exposing new areas of continental shelf and creating new opportunities for terrestrial organisms to colonize previously submerged areas. The drop in sea level also concentrated marine organisms into smaller areas, intensifying competition and driving evolutionary innovation. Many marine lineages that had been relatively stable for millions of years began diversifying rapidly as they adapted to the new conditions created by lower sea levels and altered ocean chemistry. The changing ocean circulation patterns were also affecting the distribution of nutrients in marine ecosystems. The new current systems were creating upwelling zones where deep, nutrient-rich waters were brought to the surface, supporting explosive growth of plankton and the marine food webs that depended on them. These changes in marine productivity were having cascading effects throughout ocean ecosystems. The evolution of whales during this period was closely tied to the increasing availability of small schooling fish and krill. that thrived in the nutrient-rich waters created by the new circulation patterns. The early whales were very different from their modern descendants. Many still had legs and spent part of their time on land. But as marine food resources became more abundant and predictable, some lineages became increasingly specialized for aquatic life. The evolution of baleen, the filtering system that allows some whales to strain enormous quantities of small organisms from seawater, was a direct response to the abundance of krill and other small prey in the post-Pangaea oceans. This feeding strategy allowed baleen whales to grow to sizes that would have been impossible for predators that had to catch individual prey items. The evolution of echolocation in toothed whales solved a different problem posed by life in the open ocean. In an environment where prey might be scattered over vast areas and where visibility is often limited, the ability to locate prey using sound waves provided enormous advantages. These sophisticated sensory systems didn't evolve overnight. They represent millions of years of gradual refinement, as successive generations of whales developed increasingly precise abilities to navigate and hunt in three-dimensional aquatic environments. The same processes of adaptation and innovation were playing out in terrestrial environments as the post-Pangaea world continued to evolve. The grasslands that began developing during this period created entirely new types of ecosystems that supported different communities of organisms than had existed before. The evolution of grasses themselves was a remarkable innovation that changed the face of the planet. These plants developed growth patterns that allowed them to survive grazing pressure from herbivores and periodic fires that would kill most other types of vegetation. The key innovation was the location of their growing points at or below ground level, protected from damage by thick layers of leaf bases and soil. This allowed grasses to regrow rapidly after being eaten or burned, giving them competitive advantages in environments where such disturbances were common. The spread of grasslands created new opportunities for herbivorous animals that could efficiently process large quantities of relatively low-quality plant material. This led to the evolution of specialized digestive systems, including the complex stomach chambers of ruminants that allow them to extract nutrients from grass with the help of symbiotic microorganisms. The open nature of grassland environments also favored different types of predator-prey relationships than had existed in forested ecosystems. The evolution of high-speed pursuit predators and equally fast prey animals created evolutionary arms races that drove both groups to remarkable levels of athletic performance. The horses that evolved in these grassland environments developed longer legs for efficient running, more sophisticated teeth for processing tough grasses, and enhanced sensory systems for detecting predators in open terrain. Similar adaptations appeared independently in many other lineages of grassland herbivores. The predators that hunted in these environments evolved their own specialized adaptations. Some became solitary stalkers that relied on speed and stealth to catch their prey. Others developed cooperative hunting strategies that allowed them to bring down prey much larger than any individual could handle alone. But perhaps the most significant development during this period was the continued evolution of the lineages that would eventually give rise to our own species. The primates that evolved during the breakup of Pangaea were small, tree-dwelling creatures that looked very different from modern apes and humans. These early primates were developing the grasping hands, forward-facing eyes, and enlarged brains that would eventually become hallmarks of the group. These adaptations were originally evolved for life in the complex three-dimensional environment of forest canopies, where the ability to judge distances accurately and manipulate objects precisely provided significant survival advantages. The social behaviors that would eventually become so important in human evolution were also beginning to develop during this period. Many primate species were evolving complex social structures that allowed them to coordinate their activities, share information about food sources and predators, and provide mutual protection and support. The communication systems that supported these social structures were becoming increasingly sophisticated. Some species developed elaborate vocal repertoires that allowed them to convey detailed information about their emotional states, intentions, and observations about their environment. These early experiments in social living and communication were laying the groundwork for the evolution of language and culture that would eventually become defining characteristics of the human lineage. But that story was still tens of millions of years in the future and would require many more dramatic changes in Earth's geography and climate. As we trace the ongoing breakup of Pangaea through its later stages, we can see how each geological change created new biological opportunities and challenges. The world that was emerging from the supercontinent's dissolution was becoming increasingly complex and diverse, setting the stage for the evolution of the modern biosphere that surrounds us today. The forces that had torn Pangaea apart were still operating, still reshaping the planet's surface and creating new environments for life to explore and adapt to. Each new island, each new mountain range, each new ocean basin represented a fresh opportunity for evolutionary innovation and biological diversification. The dance of continents wasn't just reshaping the physical world, it was rewriting the very rules of survival, forcing life to adapt in ways that would have been unimaginable during the stable days of Pangaea. And nowhere was this more dramatic than in the relationship between predator and prey, where the opening of new frontiers created evolutionary arms races that would define the next 100 million years of life on Earth. As the continents drifted further apart, isolated populations found themselves cut off from their relatives, facing unique challenges that demanded unique solutions. The tyrannosaurs that would eventually terrorize the northern continents were just beginning their evolutionary journey during this period, starting as relatively small, swift predators that bore little resemblance to the giants they would become. These early tyrannosaurs were experimenting with different approaches to predation. Some lineages were developing longer legs for pursuit hunting across the increasingly open landscapes. Others were evolving more powerful jaws and teeth for dealing with larger, more heavily armored prey. Still others were refining their sensory systems, developing enhanced hearing and smell that would allow them to track prey across vast distances. But the tyrannosaurs weren't evolving in isolation. Their prey species were engaged in their own evolutionary innovations, developing defenses that pushed predators to become ever more sophisticated hunters. The ankylosaurs were perfecting their body armor, evolving bony plates and spikes that could turn a predator's attack into a painful and potentially fatal mistake. The ceratopsians, those iconic horned dinosaurs, were developing some of the most elaborate defensive displays in the animal kingdom. Their massive frills and sharp horns weren't just weapons. They were communication devices, allowing individuals to signal their health, strength, and readiness to fight to both predators and potential mates. The evolutionary dance between these armored herbivores and their predators was creating feedback loops that drove both groups to remarkable extremes. As prey species developed better defenses, predators had to become larger, stronger, and more intelligent to overcome them. This, in turn, selected for even better defenses in prey species, creating an escalating cycle of adaptation and counter-adaptation. Meanwhile, in the skies above these terrestrial dramas, the pterosaurs were writing their own chapter in the story of evolutionary innovation. Some species were becoming true giants, with wingspans that exceeded 40 feet and bodies the size of small aircraft. These massive flyers weren't just scaled-up versions of smaller pterosaurs, they were fundamentally different creatures with specialized adaptations for life at enormous sizes. The largest pterosaurs developed hollow bones that were even lighter than those of birds, reducing their weight while maintaining structural strength. Their wing membranes were supported by incredibly long finger bones that could be folded and extended with remarkable precision. Some species evolved sophisticated air sac systems that helped them maintain the high metabolic rates needed for powered flight at such enormous sizes. But perhaps most remarkably, these giant pterosaurs were developing feeding strategies that had never been attempted before. Some species became aerial scavengers, using their size and soaring abilities to patrol vast areas in search of carcasses. Others became specialized fish eaters, skimming low over the expanding ocean surfaces and snatching prey from the water with surgical precision. The success of these aerial giants was demonstrating the incredible potential of powered flight in the post-Pangea world. The fragmented geography, with its numerous islands, inland seas and isolated continents, created ideal conditions for flying animals that could cross barriers that were insurmountable for terrestrial creatures. This was setting the stage for one of the most remarkable evolutionary transitions in Earth's history. Deep within the theropod dinosaur family tree, small feathered species were continuing their own experiments with aerial locomotion. These creatures were still primarily terrestrial, but they were developing increasingly sophisticated abilities to glide between trees and make controlled landings from high perches. The feathers that had originally evolved for insulation and display were being modified for aerodynamic purposes. Different types of feathers were developing for different functions. Contour feathers provided the smooth surfaces needed for efficient airflow. Down feathers offered superior insulation. Flight feathers combined strength with flexibility, allowing for precise control of lift and thrust. The skeletal modifications needed for powered flight were also beginning to appear. Hollow bones reduced weight without sacrificing strength. Enlarged breastbones provided attachment points for powerful flight muscles. The wishbone, that distinctive forked bone found in modern birds, was evolving to serve as a spring that stored and released energy during the wing-beat cycle. But the most remarkable changes were happening in the brain and nervous system. Powered flight requires incredibly sophisticated coordination between vision, balance, and muscle control. The early bird-like dinosaurs were developing enlarged brain regions dedicated to processing the complex sensory information needed for three-dimensional navigation. These neurological innovations weren't just about flight. They were creating new types of intelligence that would eventually allow birds to develop some of the most complex behaviors in the animal kingdom. The ability to navigate using landmarks, magnetic fields, and celestial cues would eventually enable birds to undertake migrations spanning thousands of miles. The social behaviors that many modern birds display, from elaborate courtship rituals to cooperative breeding systems, were also beginning to emerge during this period. The three-dimensional nature of aerial environments was creating new opportunities for visual communication and display that weren't available to terrestrial animals. Back on the ground, the mammalian lineages were continuing their own quiet revolution. Though still small compared to the dinosaurs that dominated most terrestrial ecosystems, mammals were developing innovations that would eventually allow their descendants to inherit the Earth. The placental reproductive system was becoming increasingly sophisticated, allowing mammalian mothers to nourish their developing offspring internally for extended periods. This gave young mammals significant advantages over reptiles, which had to rely on the limited resources stored in their eggs. The extended period of parental care that placental reproduction enabled was creating opportunities for learning and behavioral flexibility that were largely absent in reptilian lineages. Young mammals could learn from their parents, acquiring skills and knowledge that weren't encoded in their genes. This capacity for learning was being enhanced by the continued enlargement and reorganization of mammalian brains. The neocortex, that outer layer of the brain that would eventually become so important in human cognition, was expanding and developing new types of neural connections that enhanced memory, problem-solving, and sensory processing. The sensory systems of mammals were also becoming increasingly sophisticated. Many lineages were developing enhanced hearing abilities that allowed them to detect high-frequency sounds inaudible to most reptiles. This was opening up new acoustic niches that mammals could exploit for communication, navigation, and prey detection. Some mammalian lineages were experimenting with echolocation, using sound waves to navigate and hunt in environments where vision was limited. This technology, which would eventually be perfected by bats and dolphins, represented a completely new approach to sensory perception that had no equivalent in the reptilian world. The diversity of mammalian body plans was also increasing rapidly during this period. Some lineages were becoming specialized diggers, developing powerful claws and streamlined bodies for life underground. Others were adapting to aquatic environments, evolving webbed feet and dense fur for insulation in cold water. Still, others were taking to the trees, developing grasping hands and feet that allowed them to navigate complex, three-dimensional environments. These arboreal mammals were the ancestors of the primate lineage that would eventually give rise to our own species, though that evolutionary journey was still tens of millions of years in the future. The plant communities that supported all of this animal diversity were undergoing their own remarkable transformations. The flowering plants that had first appeared during Pangaea's early breakup were diversifying at an unprecedented rate, developing new strategies for reproduction, defense, and resource acquisition. The coevolutionary relationships between plants and their animal partners were becoming increasingly complex and specialized. Some flowering plants were evolving flowers that could only be pollinated by specific types of insects, creating mutually dependent relationships that drove both partners to greater specialization. The fruits produced by these plants were equally diverse and sophisticated. Some species developed fruits that were specifically designed to attract particular types of animals, using combinations of color, scent, taste, and nutritional content to ensure that their seeds would be dispersed to appropriate habitats. Other plants were taking different approaches to reproduction and survival. Some species were developing chemical defenses that made them toxic or unpalatable to herbivores. Others were evolving physical defenses like spines, thorns, and tough leaves that could resist browsing pressure. The competition for light in increasingly complex forest communities was driving plants to remarkable heights. Some tree species were developing trunk structures that could support canopies over 200 feet above the ground, creating vertical ecosystems with distinct communities of organisms at different levels. The understory communities beneath these forest giants were adapting to low-light conditions in creative ways. Some plants developed enormous leaves to capture as much light as possible. Others evolved climbing strategies that allowed them to reach higher light levels without investing energy in thick, supportive trunks. Epiphytes, plants that grow on other plants without parasitizing them, were diversifying rapidly during this period. These aerial gardens were creating entirely new types of habitats that supported unique communities of insects, amphibians, and other small animals. The chemical complexity of plant communities was also increasing dramatically. Plants were evolving sophisticated biochemical pathways that produced thousands of different compounds for various purposes. Some of these chemicals served as defenses against herbivores or pathogens. Others functioned as attractants for beneficial organisms like pollinators or seed dispersers. Many of these plant-produced chemicals would eventually become important to humans as medicines, spices, and other useful compounds. But during this ancient period, they were simply part of the ongoing evolutionary arms race between plants and the organisms that fed on them. The soil communities beneath these diverse plant assemblages were equally complex and important. The roots of different plant species were forming increasingly sophisticated partnerships with soil microorganisms, creating networks that could share nutrients and information across entire forest communities. Mycorrhizal fungi were evolving specialized relationships with plant roots that allowed both partners to thrive in conditions that would be challenging for either alone. These fungal networks could extend for miles underground, connecting different plants and allowing them to share resources and communicate about environmental conditions. The decomposer communities that broke down dead plant and animal material were also diversifying rapidly. Different types of bacteria and fungi were specializing on different types of organic matter, creating complex recycling systems that made nutrients available to living organisms. These soil ecosystems were becoming some of the most biodiverse environments on Earth, supporting countless species of bacteria, fungi, protists, nematodes, arthropods, and other organisms in every handful of Earth. The health and productivity of terrestrial ecosystems depended entirely on the activities of these largely invisible soil communities. The aquatic ecosystems that developed as Pangaea broke apart were equally diverse and productive. The expansion of shallow marine environments was creating opportunities for coral reefs to develop on a scale that hadn't been seen for hundreds of millions of years. These reef ecosystems were becoming incredibly complex, supporting food webs that included everything from microscopic plankton to massive marine reptiles. The diversity of coral species was exploding as different lineages adapted to different water temperatures, depths, and chemical conditions. The fish communities associated with these reefs were equally diverse. Different species were evolving specialized feeding strategies that allowed them to exploit different food sources within the reef environment. Some became cleaners that removed parasites from larger fish. Others specialized in eating coral polyps, algae, or small invertebrates. The predatory fish that hunted in these reef environments were developing remarkable hunting strategies and sensory capabilities. Some species evolved elaborate camouflage that allowed them to ambush unsuspecting prey. Others developed powerful jaws that could crush the shells of mollusks and crustaceans. The open ocean environments beyond the reefs were supporting their own unique communities of organisms. The ammonites were continuing to diversify into an incredible array of forms, some with shells that were perfectly streamlined for rapid swimming, others with elaborate ornamental features that may have served for species recognition or sexual selection. Belemnites, those bullet-shaped relatives of modern squid, were perfecting their jet propulsion systems and developing increasingly sophisticated hunting strategies. Some species were becoming specialized for catching fast-moving prey in open water, while others adapted to hunting among the complex three-dimensional structures of coral reefs. The marine reptiles that dominated these ancient oceans were reaching sizes and developing capabilities that would seem fantastic to modern eyes. Some ichthyosaur species were growing to lengths of over 60 feet, with massive heads and teeth designed for catching the largest prey animals available. Plesiosaurs were diversifying into long-necked fish eaters and short-necked mollusk crushers, each group developing specialized feeding strategies that allowed them to coexist in the same marine environments. Some species were evolving sophisticated social behaviors, possibly including cooperative hunting strategies, similar to those seen in modern dolphins. The marine crocodiles of this period were equally impressive. Some species were adapting to life in the open ocean, developing paddle-like limbs and salt-excreting glands that allowed them to thrive in environments far from shore. Others were becoming specialized ambush predators in coastal waters, developing enormous heads and incredibly powerful bite forces. These marine ecosystems were also supporting the evolution of the first marine mammals. The early whales of this period were still relatively small and retained many features of their terrestrial ancestors, including functional limbs and the ability to come onto land. But these proto-whales were already developing many of the adaptations that would allow their descendants to become fully aquatic. Their limbs were becoming paddle-like for more efficient swimming. Their nostrils were beginning to migrate toward the tops of their heads to make breathing easier while swimming. Their bodies were becoming more streamlined to reduce drag in the water. The sensory systems of these early marine mammals were also undergoing remarkable changes. Some lineages were developing enhanced hearing abilities that would eventually evolve into the sophisticated echolocation systems of modern toothed whales. Others were evolving improved underwater vision and enhanced sensitivity to waterborne chemical cues. The feeding strategies of early whales were diverse and experimental. Some species were becoming fish eaters, developing teeth and jaws specialized for catching swift prey. Others were evolving filter feeding systems that would eventually become the baleen plates of modern great whales. But perhaps the most remarkable aspect of early whale evolution was how quickly these animals were adapting to fully aquatic life. In just a few million years, lineages that had been terrestrial mammals were becoming some of the most sophisticated marine predators on Earth. This rapid evolutionary transition was being driven by the abundant food resources available in the post-Pangea oceans. The new circulation patterns and upwelling zones were supporting incredibly productive marine ecosystems that could sustain large populations of marine mammals. The success of early whales was also being facilitated by the relatively low competition they faced in marine environments. The marine reptiles that had dominated Mesozoic oceans were beginning to decline, creating ecological niches that mammals could exploit. Meanwhile, on land, the continued fragmentation of continents was creating new opportunities for biogeographic isolation and evolutionary experimentation. Madagascar, that large island off the coast of Africa, was developing one of the most unique biological communities on Earth as it drifted away from the mainland. The mammals that had been carried along on Madagascar's journey were evolving in complete isolation from their relatives on other continents. Without competition from the diverse mammalian faunas that were developing elsewhere, Madagascar's mammals were free to evolve in directions that would have been impossible in more competitive environments. The result was the evolution of some of the most unusual mammals ever to exist. Giant lemurs the size of gorillas browsed in Madagascar's forests. Carnivorous mammals developed body plans that had no equivalent anywhere else on Earth. Even the smallest mammals on the island were evolving unique adaptations to their isolated environment. The plants of Madagascar were undergoing equally remarkable evolutionary changes. Isolated from the flowering plant communities that were developing on other continents, Madagascar's flora was evolving its own unique solutions to the challenges of tropical life. Some plant lineages were developing entirely new types of reproductive strategies. Others were evolving novel chemical defenses against herbivores. Still others were experimenting with growth forms and ecological strategies that had never been attempted before. The island's unique geological history was also contributing to its biological distinctiveness. Madagascar's ancient rocks contained mineral compositions that were different from those found on other continents, creating soil conditions that favored certain types of plants over others. The volcanic activity that had accompanied Madagascar's separation from Africa had created a complex topography of mountains, valleys, and plateaus that provided a diverse array of habitats for organisms to colonize and adapt to. Similar processes of evolutionary experimentation were playing out on other isolated landmasses around the world. New Zealand, which had separated from Gondwana around 85 million years ago, was developing its own unique biological community in splendid isolation. The absence of terrestrial mammals on New Zealand allowed birds to evolve into ecological roles that were filled by mammals on other continents. Giant flightless birds became the dominant herbivores in many ecosystems. Predatory birds evolved to fill the niches occupied by carnivorous mammals elsewhere. Even the insects of New Zealand were evolving along unique trajectories. Some species were becoming unusually large, freed from the size constraints imposed by mammalian predators on other continents. Others were developing unusual behaviors and life histories that reflected the unique conditions of their isolated environment. The marine environments surrounding these isolated land masses were equally distinctive. Each ocean basin was developing its own characteristic communities of organisms as circulation patterns, temperature regimes, and chemical conditions diverged from those in other parts of the world. The Southern Ocean, which was forming as Antarctica separated from the other continents, was becoming one of the most productive marine environments on Earth. The cold, nutrient-rich waters supported massive populations of small crustaceans that formed the base of complex food webs. These Southern Ocean ecosystems would eventually support some of the largest animals ever to exist on Earth. But during this early period, they were still developing the characteristics that would make such gigantism possible. The circulation patterns that would concentrate nutrients and support massive plankton blooms were still forming. The ice dynamics that would create seasonal pulses of productivity were still evolving. But even in these early stages, the Southern Ocean was demonstrating the incredible potential of marine ecosystems to support large and diverse communities of organisms. The fish, seabirds, and marine mammals that were beginning to colonize these cold waters were already showing signs of the adaptations that would allow them to thrive in one of Earth's most challenging environments. The Arctic Ocean, which was forming as the northern continents separated, was developing its own unique characteristics. The restricted circulation and seasonal ice cover were creating environmental conditions that had no equivalent elsewhere on Earth. The organisms that colonized these Arctic marine environments had to develop remarkable adaptations for surviving in conditions of extreme cold and seasonal variation in daylight. Fish evolved antifreeze compounds that prevented their body fluids from freezing. Marine mammals developed thick layers of blubber for insulation and sophisticated behaviors for breathing through ice-covered waters. Even the plankton communities in these polar oceans were unique, with species that could remain active at temperatures that would be lethal to their relatives in warmer waters. These cold-adapted organisms were developing biochemical pathways that functioned efficiently at low temperatures, creating the foundation for productive ecosystems even in some of Earth's most challenging environments. The continued movement of continents was also creating new mountain ranges that would have profound effects on regional and global climate patterns. The collision between Africa and Europe was beginning to create the Alpine mountain system that would eventually extend from Spain to the Himalayas. These emerging mountain ranges were creating barriers to atmospheric circulation that fundamentally altered precipitation patterns across vast regions. The rain shadow effects, created by major mountain ranges, were generating new types of arid and semi-arid environments that organisms had to adapt to. The plants that colonized these dry environments were developing some of the most sophisticated water conservation strategies in the plant kingdom. Succulent plants were evolving specialized tissues for storing water during brief periods of rainfall. Desert shrubs were developing extensive root systems that could extract moisture from deep underground sources. The animals that lived in these arid environments were evolving equally impressive adaptations for surviving with limited water resources. Some species were developing kidneys that could concentrate urine to incredibly high levels, conserving every drop of water possible. Others were evolving behaviors that allowed them to obtain water from their food or from atmospheric moisture. The seasonal nature of rainfall in many of these environments was driving the evolution of remarkable behavioral adaptations. Some animals were developing the ability to estivate, essentially hibernating during the driest periods of the year. Others were evolving nomadic lifestyles that allowed them to track seasonal resources across vast landscapes. But perhaps the most remarkable aspect of life in these new arid environments was how quickly organisms were adapting to conditions that would have been lethal to their ancestors. The rapid pace of continental drift and mountain building was creating new environments faster than had occurred during most of Earth's history, and life was responding with equally rapid evolutionary innovation. The story of how our planet transformed from the unified world of Pangaea into the diverse, complex Earth we know today is ultimately a story about the incredible adaptability and creativity of life itself. Every geological change, every new environment, every challenge posed by shifting continents and changing climates became an opportunity for evolutionary innovation and biological diversification. The forces that had begun tearing Pangaea apart were far from finished. Around 180 million years ago, during the early Jurassic period, the supercontinent was entering its final phase of existence. But what happened next would make the earlier volcanic eruptions look like gentle warm-ups for the main event. The Atlantic Ocean, which had started as narrow rift valleys filled with lakes and lava flows, was beginning to resemble something we might recognize today. Seawater was flooding in from the surrounding Panthalassa, creating a genuine ocean basin for the first time. But this wasn't just water filling a crack in the earth. This was the birth of an entirely new ocean system, complete with its own circulation patterns, chemical properties, and biological communities. The spreading center that would eventually become the mid-Atlantic ridge was pumping out new oceanic crust at rates that seem almost impossible by modern standards. We're talking about seafloor spreading velocities that were several times faster than what we observe today, driven by the incredible thermal energy still being released from the mantle, superplumes that had initiated Pangaea's breakup. This rapid seafloor spreading was having profound effects on global sea level. As hot, newly formed oceanic crust cooled and contracted, it created space for more seawater. But the volume of new crust being produced was so enormous that it was actually displacing seawater and causing sea levels to rise dramatically across the planet. The result was a world where vast areas of the continental margins were flooded by shallow seas. These epicontinental seas, as geologists call them, covered areas that are now dry land across much of Europe, North America, and other continents. The English Channel, the North Sea, much of the American Midwest, all were underwater during this remarkable period. But these weren't just ordinary shallow seas. They were incredibly warm, with water temperatures that would make a modern tropical ocean seem cool by comparison. The combination of high atmospheric carbon dioxide levels from the ongoing volcanic activity and the restricted circulation in these shallow basins created greenhouse conditions unlike anything in Earth's recent history. Water temperatures in some of these epicontinental seas reached levels that would be lethal to most modern marine life. We're talking about ocean temperatures approaching those of a hot bath, sustained across vast areas for millions of years. Yet somehow, life not only survived in these conditions, but actually thrived in ways that seem almost impossible to imagine. The marine reptiles that dominated these ancient oceans were growing to sizes that dwarf anything in our modern seas. Leedsichthys, a massive filter-feeding fish, reached lengths of over 50 feet, making it larger than most modern whales. Liopleurodon, a short-necked plesiosaur, possessed a skull alone that was over 8 feet long, armed with teeth that could crush virtually any prey animal unfortunate enough to encounter it. But perhaps even more remarkable were the ecosystems these giants supported. The warm, nutrient-rich waters of the epicontinental seas were supporting plankton blooms of incredible density and diversity. Microscopic marine organisms were diversifying at rates that rival the most dramatic evolutionary radiations in Earth's history. Coccolithophores, those tiny planktonic algae that produce intricate calcium carbonate plates, were experiencing their golden age during this period. Their fossilized remains would eventually form some of the most distinctive rock formations in Earth's geological record, including the white chalk cliffs that now characterize parts of England and France. But these organisms weren't just passively floating in the ancient seas. They were actively modifying ocean chemistry on a global scale. The calcium carbonate plates they produced were removing carbon dioxide from the atmosphere and storing it in marine sediments, helping to moderate the extreme greenhouse conditions that characterize this period. The ammonites were reaching the peak of their evolutionary success during this time, diversifying into forms that seemed to defy the basic principles of engineering. Some species developed shells with complex internal chambers and intricate suture patterns that provided incredible strength while maintaining neutral buoyancy. Others evolved shells with elaborate spines, ribs, and ornamental features that may have served for species recognition, sexual selection, or hydrodynamic control. These weren't just beautiful curiosities. The ammonites were sophisticated predators and prey animals, equipped with tentacles, beaks, and jet propulsion systems that made them formidable hunters and elusive targets. Their success was so complete that ammonite shells became one of the most common fossils in marine rocks from this period, found on every continent and in virtually every marine environment. The belemnites were equally successful, though they took a very different evolutionary approach. These bullet-shaped relatives of modern squid were perfecting the art of high-speed swimming, developing streamlined shells and powerful jet propulsion systems that allowed them to outmaneuver most predators and catch even the swiftest prey. But the most dramatic changes were happening among the marine reptiles themselves. The ichthyosaurs were reaching the pinnacle of their adaptation to aquatic life, developing body forms that were so perfectly suited to marine environments that they closely resembled modern dolphins, despite being completely unrelated to mammals. Some ichthyosaur species were becoming true giants, with skulls over 6 feet long and overall body lengths that may have exceeded 60 feet. These massive predators possess the largest eyes known from any vertebrate animal, with some specimens showing eye sockets over 10 inches in diameter. These enormous eyes weren't just for show. They were sophisticated optical systems that allowed these marine reptiles to hunt in the deep, dim waters of the ancient oceans. The plesiosaurs were taking a different evolutionary path, developing into 2 distinct groups with very different lifestyles. The long-necked forms were becoming specialized fish eaters, using their flexible necks to strike at prey with lightning speed. The short-necked forms, like the massive Liopleurodon, were becoming the apex predators of their ecosystems, capable of taking on virtually any prey animal, including other marine reptiles. But perhaps the most remarkable aspect of these marine ecosystems was their incredible productivity. The warm temperatures and high nutrient levels were supporting food webs of unprecedented complexity and biomass. Primary productivity in these ancient oceans may have been several times higher than in any modern marine environment. This productivity was supporting not just the massive marine reptiles that capture our imagination, but entire ecosystems of smaller organisms that form the foundation of these food webs. Microscopic plankton, small fish, marine invertebrates, all were thriving in numbers that would seem impossible in today's oceans. The diversity of marine life during this period was staggering. Coral reefs were flourishing in the warm, shallow seas, supporting communities that included hundreds of species of fish, mollusks, echinoderms, and other marine animals. Some individual reef systems may have supported more biodiversity than entire modern ocean basins, but this underwater paradise was existing alongside equally dramatic changes on land. The continued fragmentation of Pangaea was creating an increasingly complex mosaic of different environments, each with its own unique opportunities and challenges for terrestrial life. So there you have it. The incredible story of Pangaea, a world so different from our own that it challenges everything we think we know about our planet. From that single, massive landmass surrounded by an endless ocean, to the gradual breakup that created the diverse, complex world we inhabit today, we've witnessed one of the most dramatic transformations in Earth's history. The forces that tore Pangaea apart are still at work beneath our feet right now, slowly reshaping our continents and oceans in ways we can barely perceive. Every earthquake, every volcanic eruption, every mountain range rising from the depths is part of that same ongoing story that began with the supercontinent's formation over 300 million years ago. And perhaps most remarkably, we are all descendants of the survivors of this incredible planetary transformation. Every tree in your backyard, every bird outside your window, every mammal walking the earth today can trace its lineage back to those pioneering species that endured the breakup of Pangaea and thrived in the new world that emerged from its fragments. The next time you look at a map, remember that what you're seeing is just one frame in a movie that's been playing for billions of years. Our familiar continents are still drifting, still changing, still writing the next chapter in Earth's extraordinary story, and we get to be part of it